Good morning, everyone. First, I want to thank organizer for giving me this opportunity so that I can introduce you our most recent progress on the sulfur dioxide isotopologue infrared line list. This will be helpful for atmospheric and astronomical applications, both for detections and simulations. Sorry, where should I type this? Okay. So on this page, I'll give a quick summary. Because there are some molecular spectrum are very difficult for experimentalists to measure or analyze in lab, while astronomy needs accurate infrared complete data. And we have adopted base theory plus high-resolution experimental data strategy to calculate the potential energy surface for SO₂ and construct the Ames 296K, that's room temperature line list for 5 symmetric isotopologues of SO₂. In future, we still need to calculate more higher order correction terms like non-adiabatic corrections, diagonal Bohr-Oppenheimer corrections, so that the line list will work better for high temperature and higher energies. Please remember, our work is prediction-oriented. We did have and we expected to have more mutually beneficial interactions with experimentalists. We go far beyond the simple reproduction of existing experimental data. Our predictions are being confirmed by latest experiments. So from NASA's point of view, from Herschel, SOFIA, ALMA, and JWST, this NASA, ESA, and ground-based observations, there is a golden age coming for infrared and far infrared astronomy. In this area, we are dealing with very high precision, a huge amount of very high precision spectrum data. For example, in this narrow spectral window, more than 70 features, but only half of them could be identified and assigned. In order to fully understand the spectrum you really need complete and accurate infrared line lists, especially for those molecules. SO₂ is a class 2 weight in Herschel data analysis. We need their line list so that we can eliminate their infrared contributions so the flowers can be identified. But usually, if you want your line list to be useful, you should have your line list accuracy to be at least 1.1 number or better. Starting from more than 15 years ago, we have been doing the base theory plus a high-resolution experimental data strategy. This involves exact quantum gravitational CI calculation within Bohr-Oppenheimer approximation frame on accurately determined global potential energy surface. We started from water more than 15 years ago, and a few years ago we did ammonia, and now we are doing carbon dioxide, sulfur dioxide, and hydronium cation. Next step is methane and methanol. Compared to the traditional experimental strategy, we cannot provide very high precision line positions. Usually, experimentalists are doing 10 to minus 5 to 10 to minus 8 wave number accuracy. We are not able to do that. And only experimental data can provide ultimate check on any predictions. However, when we combine the base theory available now with the selected reliable high-resolution experimental data, we are able to provide consistent, global, and complete coverage. We are able to give more reliable intensity predictions, especially for weaker bands, because we can track every individual transitions. So we provide more consistent spectral simulations at different temperature and other conditions. Also, we can generate line lists for isotopologues essentially free, and our approach can be used easily to detect errors and defects in existing experimental analysis model. I will show you some examples. Compared to our competitors, we are leading in prediction accuracies by 1 order of magnitude. Because usually our interpolations are so good, you can think in this way, we automatically fills up all the missing bands with a similar accuracy up to the highest existing experimental data. So come back to sulfur dioxide. This follows what we have done for carbon dioxide. Our carbon dioxide project was funded through the Venus Express supporting investigator programs. The Venus Express mission includes the studies for its atmospheric components, chemistry, and dynamics, where carbon dioxide constitutes more than 95% at 750 and 100 bar. Most of the goals for carbon dioxide projects have been achieved. We have 13 line lists for 13 isotopologues with line position accuracy 0.01 to 0.03 wave numbers, and they are good up to 1500 Kelvin and 18,000 wave numbers above 0 point energies. About the intensities, for most of the transitions, we are 90% or better. So first example, we have noticed that when we got our line list for carbon dioxide, we compare to the widely used HITRAN database. Please remember, in most of the databases you can access nowadays, most of them data in those databases are not really measured in lab. The traditional way is the spectroscopists measure a few dozens or hundreds of transitions and feed them to the effective Hamiltonian model. Use that model to derive a whole set of transitions and put that into the database. That's the data you have in the database. When we compare our line list to the database, we found that there exists a big discrepancy at 1.1 micron, 9,000 of number. Our predictions are 2 orders of magnitude stronger than the old data in HITRAN. Triggered by this big discrepancy, Russian spectroscopists carried out new measurements and confirmed our predictions are correct. Because in the old HITRAN model, the effective dipole moment value was totally wrong because there were no experimental data standing behind that. It was a purely guess. So they have fixed the problem. Now our predictions have a very excellent agreement for that vibrational bands. Other predictions have been confirmed by recent experiments. Again, I want to mention that we have 13 line lists for 13 isotopologues, especially for those missing bands and minor isotopologues. We provide very consistent, reliable, accurate alternatives. Now come back to Venus. After we got the carbon dioxide spectrum, we noticed that there still exists a spectral region where SO₂ have a strong absorptions, but CO2 is pretty weak. For those regions, we do need complete, accurate line lists, but the available data for the region are quite limited. So what we have done, I don't have time for details. Basically, we started from ab initio calculations. And then we calibrate, or we say refine our potential energy surface with a few hundreds of selected energy levels derived from HITRAN database. On the refined surface, we are able to reproduce most of the transitions in HITRAN database to plus or minus 0.02 wave number, accuracy for 9 positions, and the intensity deviations within 10%. So here I show you the comparison of limited available hydrogen data by green lines that's available in HITRAN and the continuous complete coverage of our line list. As I said, usually our interpolations and the extrapolations are so good we can automatically fill up all the missing bands there with similar accuracy. Now I will give you the examples. Simply reproducing data doesn't help much. Only prediction matters. Because in our refinement, we only have the experimental data information of main isotopologue included in HITRAN, but HITRAN knows nothing about the new experiments after 2008. So the new experiments carried out by Uniletkov group provide us very good opportunities checking our predictions. First example, mu2 plus mu3 at 1870 wave numbers. You can compare our predictions to observed peaks, basically peak by peak, line by line. Also, you can compare those grass-like area. That's the hot band from nu2 to 2 nu2 plus nu3. We can also match many of those grass-like peaks as well. A second example at higher energy, 3400 wave number, that's a 3 nu1 p branch band. Observed spectrum in the middle, our predictions at the bottom. All the main features, one by one, peak by peak. Third example coming this year, nu1 plus nu2 plus nu3. I make the comparison in this way. On the top observed spectrum, you can see we match one of each of them with maybe 0.01 wave number deviation on 9 positions. Okay, this is the accuracies we have confirmed. We know we will have this kind of accuracy. Just needs the confirmation from the experimental side. Another kind of extrapolation is for isotopologues. During our refinement, only the data in HITRAN from main isotopologue was included. However, on our refined surface, we are able to reproduce the 646, that's a Sulfur 34, its band origins with similar accuracy, essentially the same accuracies as we have for the main isotopologue. So we know the line list we calculated for the 646 carries a similar accuracy as we have for the main isotopologue. So we continue calculate the other 3 line lists for 636, 666, and 828. That's the 5 most important symmetric isotopologue of SO₂. Here are the spectrum, and we hope them will be helpful to facilitate the lab analysis and the modeling. Up to now, these line lists are based on J from 0 to 80 calculations. Energy levels may as high as 8,000 Webb numbers. However, because of the very high density of the states, it is difficult to converge the high-lying energy levels at 8,000 Webb numbers or 10,000 Webb numbers. This caused some noise when the temperature rises. Our line list will exhibit some instability. Up to now, we suggest the line lists are good for 500K up to. The last example I want to show you is the existing database, the HITRAN and CDMS. When they did the fit to the observed data, they didn't include any experimental data with quantum number Ka higher than 23. But this model, the fitted model, was used to derive energy levels and transitions with Ka as high as 35 to 45, almost doubled. This directly leads to the errors in existing HITRAN database and CDMS database. These points, the discrepancies, have been proven to be the problems due to this over-extrapolation along Ka. Last year, UNESCO group published a new effective Hamiltonian model. They included higher Ka quantum number data. Now we have a much better agreement, as shown by red dots. Okay, I will just talk to this page. This may help partially explain the discrepancy we found in the intensity of the main isotopologue pure rotational band. If you compare to the full HITRAN and CDMS model, you can find like 20% to 60% intensity deviations. This is a very big deviation compared to what we can have if we compare to the experimental data set. That's the experimental data set behind the model. We compare to that experimental data set, intensity agreement is 1% to 3% off. So we suspect there is some problems with extrapolations. I will ignore this one. This is another example to show the possible over-extrapolation for the main isotopologue. At the end, I want to tell you that both carbon dioxide and sulfur dioxide line lists are available to download at this huang.cit.org website. The study was funded from NASA APRA program and the Venus Express supporting investigator programs. Thanks for your attention.